we're going to talk about solving separable first-order differential equations. We call a first-order differential equation, written in this standard form, dy dx is some function of x and y, separable if we can write this function f of xy as a product of some function of x times some function of y. Let me show you some quick examples of what constitutes a separable differential equation. If we write dy dx equals x squared y squared, of course that's separable since here we have a function of x times a function of y. Sometimes it's not quite as obvious that an equation is separable if we write dy dx equals, for example, x over y plus x squared y. With just a tiny bit of algebra, we can see that we can write this as x over 1 plus x squared times 1 over y, and recognize this as a separable equation. So these are both separable differential equations. If we have something simple like dy dx equals x plus y, there's no way to write this as a separable differential equation. Of course, this is a relatively simple first-order linear differential equation, and we've already learned how to solve this type of differential equation. When we have a separable differential equation of this form, dy dx is some function of x times a function of y, we can rewrite that by dividing by k sub y first and then moving h of x over to the other side. We can rewrite it in this form, and then we continue and we just give new names. This is to match the book's notation. M of x, that's the minus h sub x from before, plus n of y dy dx equals 0. So this is a different way of writing a standard form for a separable differential equation. This is a useful form because we can just integrate both sides, left and right. Of course, the integral of m of x is just whatever that integral is. And to integrate n of y dy dx, here we're integrating with respect to x. We just get whatever the integral of n of y dy is. That's true since when we differentiate with respect to x, this integral of n of y dy, what we get by the chain rule is precisely n of y, that's the derivative of this thing with respect to y, times dy dx. So the derivative of this integral is just n of y dy dx. So when we're integrating both sides, this is what we get. And of course, when we integrate 0, we just get some arbitrary constant. Of course, there's going to be an arbitrary constant associated with each of these integrals. We can imagine moving them all over to one side at the end so that we end up with just a single arbitrary constant in our final equation for the solution. Now notice that when we have an equation in this form, m of x plus n of y dy dx, if we treated this derivative dy dx as a quotient, which of course it's not, but we just formally think of it as a quotient and multiply through by dx, we can write it in this form, which is actually pretty standard in differential equations. This is called the differential form of this differential equation. What does this mean? Well, it has the meaning no different from the previous equation. So if you see an equation written like that, just formally divide by dx and you'll get an equation like this. Now, one reason it's useful to write the equation in this form is one thinks of solving it by just slapping on integral signs. Integral m of x dx plus integral ny dy equals the integral of 0, which is c. Of course, that's the same thing we had before, so we know that that gives us the correct solution.